All right. Good morning, OffensiveCon. My name is Jason. I'm a security consultant at MWR. And what I want to be showing you guys today is how we can fuzz 3D acceleration and eventually pwn it with some self-imposed restrictions to make it a bit more interesting. The idea with this talk is to cover a lot of breadth, so I'm asking you to really stick by me with this. So first off, what is 3D acceleration as it pertains to VirtualBox? So VirtualBox makes use of a technology called Chromium, which is essentially just an abstraction layer over OpenGL. And this accepts Chromium messages, which define graphical operations. And it's within the parsing of those messages that the actual bugs sit. Now, Chromium can be used as a standalone TCP server, or as in the case of VirtualBox, an embedded software component. Now, guest editions can essentially be thought of as a collection of services, where 3D acceleration is just one of them. And the way that you interact with these services is by speaking the HGCM protocol. And this protocol can be spoken to the host from the guest via device files within the guest. And this is all accessible to unprivileged guest users. Now, one of the main interfaces exposed by these services is a function called SVC call. So you'll find them in all of these various guest edition services. And they essentially receive the HGCM messages, take out some parameters, and do something with that. So a Chromium message will be one of these parameters. So quick look at how we can fuzz VirtualBox or 3D acceleration. Essentially, there's not a whole lot that we need to actually interact with Chromium. If we want to, basically we just need to initialize the Chromium server, which there's a convenient export for from the shared CR OpenGL module. We need to be able to connect, disconnect, and send Chromium messages to basically simulate everything that a guest operating system would do when interacting with 3D acceleration. Now, looking at what a Chromium message looks like, how to craft these, on the left, you'll see two Chromium messages. And one of the biggest things here in this message is the CR message opcode's message type. So this prompts Chromium to execute an opcode handler. So you specify opcodes in this message. And there's a one-to-one relationship between opcodes and opcode handlers. So CR unpack or CR unpack extend will receive these opcodes and call the appropriate opcode handler, which will read some input from our Chromium message and pass that on to the relevant dispatch method. Now, all of the bugs associated with Chromium are usually within these opcode handlers or within these dispatch methods. Now, basically, we're generating a bunch of input because we want to fuzz 3D acceleration. So the main things to take away from figuring out what to do with that input, basically adjusting some of the input, is making sure that our message type is set to CR message opcodes. Basically, it can get quite complex when specifying multiple opcodes. So maybe you're interested in doing something more one-dimensional, so fixing the number of opcodes to 1. When looking at the opcodes, so 3 and 4, we want to make sure that they're within range. Specifying a dead opcode doesn't mean anything to us. We won't be hitting any code paths. And if you want to get really smart with this, you can look at the input parameters or input values that you're giving for that opcode. Maybe look at the data types. There's a relatively easy to follow convention within opcode handlers for what various values or variables are used for. And eventually what we're going to do is we're taking that Chromium message and sticking it into client write, and maybe the bugs fall out. So ideas regarding developing a fuzzle like this, take into consideration that there's little more than 550 opcodes, which I think is a relatively big attack surface, looking at it from an unprivileged guest perspective. And essentially what all of these messages do is they manipulate the state of Chromium, all right? Up to this point, most of the bugs that have been identified have been one-dimensional. So single opcode results in an opcode handler or dispatch method being called, bug gets triggered. But I do think that some of these are, these are dying out fairly quickly. And we're definitely going to have to start thinking about some of the more intricate things about the state of the Chromium server. For example, a bug that still needs to be mitigated basically was this convoluted process of forcing Chromium into the state to trust a pointer supplied by a guest operating system. So that happens too. Now, I'm a fairly novice vulnerability researcher in terms of fuzzing. So for me, I just kind of use standard AFL to see where that takes me. And what I can say is that initialization of the Chromium server takes a whole lot of time, 65 milliseconds, which, I mean, if you're working with in-memory fuzzing, this problem can be overcome. But despite that, if you're really interested in building an AFL fuzzer for 3D acceleration, it's as simple as pointing configure to AFL GCC and AFL G++. So something that I will say is that definitely do this. Comment out RTL log create within that source file. So Chromium, upon initialization, creates a log file, writes to it. So if you're fuzzing 3D acceleration, you're going to fill up your disk space. Or you can be this idiot and create a bunch of cron jobs that run every 20 seconds to clear a folder. It took me a while to find out that this was the problem. All right, so debugging VirtualBox is very tedious. There's this weird thing where if you're focused on a virtual machine and you hit a breakpoint, the keyboard and the clipboard just break, and that really sucks. Testing production also sucks because of debugger checks, so VirtualBox just says no. And I wanted to get around this to really facilitate making my, my exploit efforts a lot easier. And the idea that I came up with is basically creating this little standard interface that consists of connecting, disconnecting, and making HGCM calls. Now, how that interface is implemented on the host, that library will load the relevant DLLs, read the export methods or get the exported methods, and use SVC call to simulate connecting, disconnecting, and making HGCM calls. Now, SVC call isn't exported, but if you initialize Chromium at a higher level, you can kind of smuggle out that pointer, which is great. You can do this for debug and prod. And on the guest operating system, this interface is essentially implemented as a set of driver calls, right? And what I ended up with after making this is basically this workflow. I exploit the debug libraries. I can debug the symbols, that's great. Then I update my exploit to target the prod libraries, just update offsets. I can still debug this because I'm not running in VirtualBox. And then I turn my VM on for the first time, which has sped up the process quite a lot. Now, a lot of the code related to this library that I wrote, and also some example fuzzing harnesses. I'm planning to release all of these on GitHub, so soon TM. All right. So poning VirtualBox and looking at these two bugs. Now, throughout the next two sections, there's going to be a couple of interesting exploit primitives that we can use to facilitate our exploitation. For example, we've got this amazing feature in Chromium where we can buffer Chromium messages, and we can make those buffers arbitrary sizes, meaning that we can perform arbitrary size allocations. We can write to those allocations to a byte of granularity, and when we execute those buffers as Chromium messages, they get freed. All right, so we can free and allocate. And all of these buffered Chromium messages are backed by an object, which I'll refer to as a service buffer. And service buffer objects hold a pointer to the Chromium message through p-data. Now, if this is research that you're looking into, you're bound to come across methods like SVC get buffer and SVC call to better understand how these buffers are used. So let's first look at our info leak. So 2019, 25, 25. I reported this, but Nicholas unfortunately beat me to it. This was an out-of-bounds read in CR unpack extend get attrib location. And what you can see on the right is, on top right, is a Chromium message, and we have this value that we're providing called packet length. All right. Packet length in the opcode handler is used in set return pointer and set write back pointer in those macros. Now, what those macros translate to is a call to CR memcopy, which is just a memcopy wrapper. And the offset is added to CR unpack data, which is a pointer to our Chromium message. And at this specific instance, CR unpack data is actually pointing to packet length. Now, the destination for this copy are two global variables, in this case, return pointer and write back pointer. And after the message is executed, return pointer and write back pointer will be returned to the guest. Basically meaning if we can make packet lengths very, very large, we can read into adjoining memory. And in total, because both of these two variables or objects are 8 bytes in size each, we get to leak 16 bytes. Now, the target for our info leak here is a CR client object, which represents an active connection to Chromium. And one of its members, called current context info, is initialized to point to crserver.mainContextInfo, which is a global variable. CR server is a global variable. So if we can leak that object or leak that member in that object, we've got a pointer in the shared CR OpenGL module. So subtract some offset, and we've defeated ASLR. So calculating our value for packet length is fairly straightforward. We're targeting CR client objects. We can abuse our ability to make arbitrary sized allocations to target that low fragmentation heap bucket. And the idea here is to make numerous connections. So you're kind of limited to 64, but that's not a problem. And then we're just going to keep on sending our malicious message. If it doesn't work the first time, just mash X. And the way we're going to calculate this is fairly straightforward. Start of our Chromium message to start of CR client, that's 810 hex. Into our Chromium message, packet length is 10 hex, and into the CR client object, that's 20 hex. So do the math, we see packet length is 831 hex. So how do we execute code, or what will be our code execution primitive? So 2019-2548, this was an integer overflow. And at one, you can actually see a patch that was introduced earlier. So that entire check there didn't exist, which was very convenient at the time. And two, we can see that message length gets calculated by taking a size of RP, which is 38 hex, and then adding multiplication between bytes per row and height, both attacker controlled from the VM. And then three, message length is used to allocate memory. So basically, if we can craft bytes per row and height in such a way that the allocation is smaller than the object size, we can write into adjoining memory when the object gets initialized. And something that you'll see soon is that the object gets entirely initialized by values obtained from the guest operating system. So quickly looking at our restrictions, bytes per row is not supposed to be, it's supposed to be smaller than an eighth of unsigned int max, greater than 0, height smaller than eighth of an unsigned int. So let's choose message length to be 20 hex, meaning that we'll be writing 18 hex into adjoining memory, if this works. And just choose an arbitrary value, well, for height as 8. And we can see that the math says it. We're kind of meeting all the criteria that the patch forces us. So our target object for this is that same is a service buffer object. Surprise, surprise, we've already did the math for targeting 20 hex allocations. And the reason we're interested in this object is because it can give us out of bounds and arbitrary write primitives if targeted correctly. Now, the interesting members of this object is an ID. That is a reference that we hold to that object. The size, basically when you update this buffer, the size is used to make sure that you're not writing out of bounds. So if we can somehow increase that to some massive size, we can write into adjoining memory. And obviously, if we can somehow control p dot, then we can update into arbitrary memory locations. So just to give you an idea of what we're working with, on the left we have like a hypothetical empty piece of memory followed by a service buffer. And on the right is not really that important, just to give you an idea of everything that gets initialized with RP. Now everything inside that initialization is controlled by us, except for the message type or the header type. And after initialization, it looks something like this, all right? What we've done is we've overflowed this, the integer, we've allocated less memory than is necessary for the object, and skip pixels, row length, format, and type all corrupt the heap header of our service buffer that we're targeting, and pixels, which is an 8-byte value, will corrupt UID and UI size, okay? And this is great because we corrupted UID with deadbeef, so that's something that we know we can use that as a reference to reference that buffer. And we've made UI size be largest that it can be, and that basically means that the service buffer within our new buffered Chromium message range, we can write into it. So what we can do is carefully write into various offsets that we've calculated that would typically be the place where a UID would be. So we can keep on doing that and maybe just write like beef dead, and we can keep on checking that. So we can do a write, we can check if that buffer exists. Now, eventually what will happen is if we manage to get one of these, then we can fully control it by, now we have a, we write into its ID, we overwrite p-data, we have an arbitrary write primitive. So this is typically what our configuration looks like at this stage. We have a partial control buffer, which is sufficient to control another buffer, fully control another buffer. So we modify partial buffer to write into SVC full. We adjust SVC full's UI size and p-data through our partially controlled service buffer. And then finally what we can do is we can write, well, or update SVC full to write whatever we want, wherever we want. Now, we've got 2 bugs. Let's see what we can do in terms of exploiting them. Now, we've defeated ASLR with our first bug, and we've obtained an arbitrary write primitive. I want to try 2 things. Because VirtualBox uses very old compiler technology, it's very boring just trying to do, well, it's very boring just trying to bypass some of the exploit mitigations because it has a lack thereof. Now, we want to try and break out without shellcode, and we want to avoid requiring any kernel 32 offsets. And for this, we're going to need an arbitrary read and a command execution primitive. So in this scenario, we're attacking a Windows host from a Linux guest. Now, what I mean by shellcodeless is that we can target the actual dispatch table that gets called in opcode handlers. Now, the signatures for the functions in that dispatch table look awfully similar to the things we want to end up executing anyway. So in this case, I'm showing you an example of winexec. How that might typically look is we're sending a window create extend opcode. We've overwritten CR unpack dispatch window create. It points to winexec now. And in our message, we can specify parameters that will get parsed out in the opcode handler and eventually passed to window create, which is now pointing to winexec. And we can use this for quite a few things, as we'll see now. Next, we want to create an arbitrary read primitive using this shellcodeless technique. For this, we're going to target a CR client object again, just because it has a really nice member called con, which is a CR connection object. So certain Chromium messages after execution, the responses are buffered, and the response is pointed to by phost buffer and the size thereof kept in CB host buffer within con. Okay. So if we can leak CR connection or con within a CR client object and use our arbitrary write against that, we can basically fake buffered responses, eventually leading to reading arbitrary memory. Now, a really interesting function that we're going to use for this is server client get. So this method takes a client ID and a pointer, or second order pointer for this. And it basically retrieves a pointer associated with the client ID that was provided, and takes that pointer and writes it to PP client. Now, what makes this interesting is that when Chromium messages get modified in transit, so during that whole transaction, you will get the modified version. So if we can somehow have PP client point to our Chromium message, then we can leak arbitrary CR client objects. The way we're going to do this is by attacking the delete fences NV function in the dispatch table. It accepts an integer and it accepts a pointer, an int pointer, which kind of looks like a CR client object to me. So what we can do is we can now specify a client ID, and in the opcode handler, they're basically going to use data pointer to retrieve a pointer to our Chromium message. So when the delete fences gets called, we're actually passing server client get our client ID and a pointer to our message. After execution, it gets returned back to us. Now, what we're going to do now to actually leak a connection or the con member here is we're going to fake a Chromium message and basically have it stretch over across a CR client object. The idea here is to point our fully controlled service buffer to a couple of allocations before the target CR client object, and then just write a opcode message to it and have it execute, and we'll receive the content of that message, which will contain the entirety of that CR client object, containing pointer to the CR connection object. Now, There's a little problem with this in that it's not as elegant because we don't know what that memory is used for. We can't just write to it. So my idea here is to get an initial CR client object's address, make a bunch of CR client allocations, and then get those addresses and kind of like work until I have an address that's within 4 allocations, and disconnect that client and then point our Chromium message buffer to that client. We know that that memory is free now, and we're just going to point it there. So our fully controlled service buffer will then point to that earlier allocation. UI size will extend to pass the CR client object, and then we write our opcode message, execute. We now have a pointer to a CR connection object. Now there's a couple of drawbacks with this. SVC full, when the message gets executed, P data gets freed, meaning that we've got a double free condition. We've disconnected the CR client object and then executed a Chromium message. But for that purpose, I basically just spray the heap again and hope for the best. We also lose our arbitrary write, because we've kind of like used SVC full now, and it will be freed. But the thing is, we can basically reuse our partial buffer to do this exact same thing, and regain our fully controlled SVC buffer. So using the address of that CR connection object, we can now basically manipulate P host buffer and CB host buffer as long as we never disconnect that client. So we can manipulate P host buffer and CB host buffer to now read arbitrary memory. So as for a command line execution primitive, there's this convenient function called CR spawn. It is within the same module as CR memcopy, which is used by shared CR OpenGL, meaning that just through our arbitrary read and attacking the import address table, we'll eventually end up with a pointer to CR spawn. And this does, on Windows, it does create process. On other systems, it uses execvp. And we're going to use bounce info CR in the dispatch table to point to this function. Now what this does is it basically receives, basically what's going to happen here, the CR spawn method, bounce info CR is going to accept some value, and it's going to be interpreted as a pointer, or it's going to give a pointer to a Chromium message to CR spawn, and CR spawn is going to dereference that pointer as another pointer. So, and then that is eventually going to be our command line. So the idea is to create a CR client object, disconnect it. We're okay, after CR spawn, that memory is not going to get freed. So we'll just write all of our arguments to that CR client, old CR client object's memory, and then add that to our Chromium message. And when we call this dispatch method through using the relevant opcodes, we'll be executing OS commands. So we managed to convert our arbitrary write and info leak into an arbitrary read through attacking the dispatch table and creating fake service buffers. We obtained the address of CR spawn using our arbitrary read, and we haven't executed shellcode or used kernel 32. All right, mandatory demo. I'm hoping calc will spawn on the screen. All right. It worked. Okay, but is that, I'm running it still, so. Okay, now. All right, and yeah, any questions? Shit. All right.
I'm sorry.
Hi. Entirely depends on Chromium. Have you tried this on other software that relies on Chromium or is built upon Chromium?
So the thing is, I only know of 3D acceleration in VirtualBox that makes use of Chromium. But what I will say, something to take out of this is that a lot of the stuff regarding fuzzing and so on, that carries over to other components of VirtualBox itself. So because the other guest edition services expose the same interfaces, and there might be a similar strategy that you can actually take with device simulation in VirtualBox. But as for other products that use Chromium, I'm not sure. All right.
Any more questions? Okay, then I think that's it. Thank you.